So I'm going to get started. If you haven't already, make sure you sign in up here on the sign-in sheet. So worksheets 2, 5, 6, and 7 are available on Brightspace as quizzes. They are due on the 11th. The test on chapters 1, 2, 5, 6, and 7 will be on the 11th. And homework number 1 is also posted on Brightspace. It's problems from your book. You need to go to the exercises section at the end of each chapter for the problems. And that is also due on the 11th. The test will be in person in here. It's going to be multiple choice test. The whole class period on the 11th will be spent on the test. Also for the test, you will get 1 sheet of notes that you can put whatever you want on it to use for reference, but only 1 sheet. Front and back. Yeah, front and back. So we're starting up chapter 5 on light and the electromagnetic spectrum. So light is electromagnetic radiation. It's oscillations of electric and magnetic fields. It's created by moving charged particles. And this is not just the light that we can see. So like right now, the projector is generating light, which is hitting the screen, bouncing off, and entering your eyes. But there are other types of electromagnetic radiation that are exactly the same thing, just outside of the range of frequencies or wavelengths that our eyes can detect. So things like X-rays, infrared light, radio waves. So I'm making, radio waves, infrared, ultraviolet, X-rays, and gamma rays are all different types of light. They're all the same thing. They're just different energies and different wavelengths. So radio waves are really long waves. They're slow wiggles. Use them all the time. I'm using them to go from slide to slide right now. So this device emits electromagnetic radiation in 2 ways. 1, it emits red light as a laser pointer. And 2, when I press a button, it sends out a radio signal to a detector over there to tell it to skip to the next slide. So that's electromagnetic radiation. Now, light is a wave. It's an oscillation of electric and magnetic waves. Because it is a wave, it is characterized by a wavelength, the length, the distance between 2 peaks, and the frequency. So this is moving along. So if you were standing in one place, the frequency would be how often a peak passes you. And so the speed of light, the speed of any wave is going to be its wavelength times its frequency. The speed of light is its wavelength times its frequency. But the speed of light is the same for everything. As long as it's traveling through a vacuum, the speed of light is 300,000 kilometers per second. It is the same at all frequencies. So light acts like a wave. It undergoes interference. So you can have light waves. When 2 light waves combine, they add up. You can have light waves that are timed such that they cancel out, or light waves timed such that they get bigger. So if you've ever seen the sort of rainbow film of oil on water or on a bubble, that's caused by interference. It's the wavelengths that bounce off the inside of the bubble interacting with the wavelengths that bounce off the front of the bubble, basically. And if the difference in distance is such that some wavelengths interfere constructively, they add up, and other wavelengths interfere destructively, they cancel out. And so some colors, because colors are a function of wavelength, end up bright and others end up dim. We see other things we expect from waves: reflection, refraction, which is how light bends when it enters a material where the speed of light is different. So if you've ever seen that your straw looks bent in a glass of water, that's refraction. And diffraction, which is how light bends around sharp corners or objects, or spreads out when passing through thin slits. And we see the Doppler effect, which is an effect caused by movement of the source of a wave, or relative movement of the observer and the source. But light also will sometimes act like a particle, because the universe is confusing. And so light appears to come in little lumps of energy called photons that are tied to the frequency. So the energy is Planck's constant, which you don't need to know, times the frequency. So the higher the frequency, the higher the energy of these little packets. And this was actually discovered, the research that discovered and explained this was done by Einstein on his studies of the photoelectric effect, and is actually what he technically won a Nobel Prize for, because of weird politics within the Swedish scientific community at the time. So light acts as a particle. We get the photoelectric effect, where if you shine light on a surface, it will only knock electrons free if the frequency is high enough, and the energy of those electrons is dependent on the frequency, not the intensity. So if you shine a brighter light on a surface, you'll get more electrons knocked free, but they won't be going any faster. And we also see light be deflected by gravity. Light is bent by gravity. And so that's something you expect from particles, not so much from a wave. So one of the unique things about light as a wave is that it is one of the few waves out there that its medium is sort of itself. So it can travel through nothingness or a vacuum. So electromagnetic radiation allows the transmission of energy throughout space without a physical connection. And that's through varying electric and magnetic fields. So what's vibrating are the electric and magnetic fields. And an example of this is visible light. So here is a galaxy as seen in visible light. That light is generated in that galaxy and travels through a whole bunch of empty space to eventually reach a telescope. So waves transmit energy without moving stuff. So what waves can do is by moving vibrations of material, transmitting vibrations of material from one thing to another, or transmitting oscillations of something from one thing to another, they can transmit energy without the physical transport of material. So when I'm talking, you're hearing me, energy is coming from my mouth to your ears, and it is doing this via oscillations in the air, but the air from my mouth is not actually reaching you. It's, probably not getting any further than about here. I'm just vibrating the air back and forth. So an example is a water wave. The water primarily just moves up and down, but the energy is transmitted along the surface. The wave travels along and it can transmit energy, but the water itself doesn't really move. It moves a little bit up and down, but it doesn't move very far. And similar things happen with other waves. So when we talk about waves, we can describe them with either a frequency or a period. So a wave, you could describe a wave with the frequency, which is how many oscillations you get per second, or how many cycles per second, kind of thing. The number of wave crests that pass a given point per second, while the period is the time between each crest. And there's a simple relationship between frequency and period. The period is 1 over the frequency. The frequency gets used a lot more than the period in any sort of wave that happens relatively quickly, like light, because the period of a light wave is a tiny, tiny number. So we tend to more often talk about the frequency. And also because this relationship is a little nicer. So the wavelength is the distance between successive crests in a wave, and the velocity is the speed at which these crests move. And velocity is equal to wavelength over period, because it's, speed is distance over time. But because frequency is 1 over period, velocity is equal to wavelength times frequency, which is the more useful relationship. So if you know the frequency of a light wave, you can figure out its wavelength, and vice versa. Because you know the speed, because that's fixed, that's the speed of light. So waves all undergo certain properties. Diffraction is the bending of a wave around an obstacle, like here, where we have water waves hitting a breakwater, and the waves bend around this breakwater, so they're not just continuing straight, they're bending into this space as well. And interference is the sum of 2 waves. So here we have what would be called destructive interference, because these waves are out of phase to an opposite. When one is going up, the other is going down. So they cancel out some to create a smaller wave. So if you've got active noise canceling headphones, that's what they do. Active noise canceling headphones record the noise from outside and play it back upside down so that it cancels out the noise from outside. So it uses what's called destructive interference. And so this is the sum of 2 waves. And you could have both destructive, where the 2 waves are out of sync with each other and cancel out, and constructive, where they're in sync with each other and add together and get even bigger. And often when you have an interference, you'll have constructive in some places and destructive in other places. Because you have like 2 sources, and when they line up in one way, they add up, and when they line up in another way, they cancel out. And you get patterns. Water waves, sound waves, etc., all travel through a medium. So water waves travel through water. Sound waves travel through air and other things. Electromagnetic waves travel through the electromagnetic field. They don't need a medium, because the changing electric field creates a magnetic field, and the changing magnetic field creates an electric field. So it sort of feeds back into itself and travels on its own. It doesn't need some stuff there to do it. And the way we create electromagnetic waves is we accelerate charged particles. The simplest way is, you wiggle a charged particle up and down, and that'll create an oscillating electric field. There are other ways we do it that involve atomic transmissions and other things, but they all boil down to accelerating charged particles at some level. Magnetic and electric fields are inextricably intertwined. They're actually the same thing. The magnetic field and the electric field are the same force, just slightly different aspects of it. They're tied together by relativity. So like if you work out magnetic fields with special relativity I mean, if you work out electric fields with special relativity, you end up getting magnetic fields out when things move. And so a magnetic field, like the one from the Earth, will exert a force on a moving charged particle. And a moving charged particle will create a magnetic field. So here we have the Earth's magnetic field. Charged particles that interact with the Earth's magnetic field have a force act on them. They effectively end up spiraling around the magnetic field lines and usually end up hitting the poles, or hitting more towards the poles. They can get trapped actually and bounce back and forth in what are called the Van Allen belts. So electromagnetic waves are oscillating electric and magnetic fields, where the changing electric field creates a magnetic field and the changing magnetic field creates an electric field. And they're at right angles to each other. So this is the magnetic field, this is the electric field. And they oscillate back and forth like this. And the electromagnetic spectrum covers a large range of different wavelengths. There's different types of radiation. They depend on energy and wavelength. And the different wavelengths interact with the atmosphere. So this shows what wavelengths actually make it through to the ground. And it's actually quite limited in the range that makes it through. The only wavelengths that penetrate the atmosphere are visible light. It's in what's called the optical window. It's actually visible light and a bit on either side. There's a bit of ultraviolet and a bit of infrared that make it through. And there's also a radio window. So radio waves can also be observed on the ground. And this is why, since we started developing radio astronomy, it's been very popular and we've been doing a lot of it, because that's, another wavelength, we can look at the sky, but also radio waves are much less affected by things like weather and whether or not it's daytime, stuff like that. So radio telescopes work under more conditions than optical telescopes. Because the waves are longer, they can basically pass through a lot of the stuff in the atmosphere that would, like a cloud is a bunch of tiny water droplets to a radio wave that just go through. If stuff is small enough, big enough wavelengths will just ignore it. And that's actually one of the more helpful aspects of things like radio waves and infrared. You can see through dusty clouds and stuff like that. Because the waves just diffuse around these small objects. They bend around them because they're so much bigger. So for X-rays, gamma rays, ultraviolet light, and infrared light, you need to get above the atmosphere. So the atmosphere blocks most wavelengths. So once we were able to start putting satellites up in orbit that could study other wavelengths, it greatly broadened the range of things we could see. So different colors of light are distinguished by their frequency and their wavelength. And the frequency and wavelengths are inversely proportional. Higher the frequency, shorter the wavelength. And the visible spectrum is only a small part of the total electromagnetic spectrum. So, radio waves have frequencies down in the kilohertz range. Like AM radio is hundreds of kilohertz. FM is in the megahertz. Visible light, so that's 10 to the third, 10 to the sixth, that kind of range. And the wavelengths can be as long as like a kilometer. Visible light ranges in wavelength from 700 nanometers to 400 nanometers. So, remember that a nanometer is 10 to the minus 9 meters. So it's a billionth of a meter. So 700 to 400 billionths of a meter. And that's 4.3 times 10 to the 14 to 7.5 times 10 to the 14 hertz. So very high frequencies. And then there's, a whole range in between. There's infrared, radio waves, microwaves are part of the radio here, and then ultraviolet, X-ray, gamma ray. So different parts of the full electromagnetic spectrum have different names, but they're really all the same thing. We've just named different chunks of them. It's like red versus blue. Those are different frequencies of light, but they're still light. It's just, we go well beyond that. So radio waves, these are the radio waves, AM, FM, there's gigahertz, 100 gigahertz, the microwaves are up here. The microwaves in your microwave oven are about, their wavelength is about 12 centimeters. It's a specific wavelength that water reacts to. So they're always the same. That's how it heats up. And then we have the infrared, from the far infrared to the near infrared. This is what the James Webb Space Telescope is looking at. This sort of this end of the infrared. The visible, the ultraviolet from near to far, which overlaps with soft X-rays. X-rays go from soft to hard. Hard X-rays overlap with gamma rays. There's a whole bunch of weird, bizarre stuff going on in the terminology between X-rays and gamma rays. But in general, gamma rays are the higher powered ones, X-rays the lower powered ones. The line is sort of fuzzy because different people use different naming conventions for where to divide it. But again, they're all the same sort of stuff. So the atmosphere is only transparent at a few different wavelengths. The visible, the near infrared, and part of the radio spectrum that has frequencies that are higher than the AM radio band. Below the AM radio band, there's actually an ionized layer in the atmosphere that the radio waves will bounce off of. But this is actually why AM can travel very far on certain days, and it's how shortwave radio travels so far. This means that our atmosphere is absorbing a lot of the electromagnetic radiation hitting it, and that astronomy and other wavelengths has to be done above the atmosphere. And in that image, the horizontal scale was logarithmic. So in this, the horizontal scale was logarithmic. So each tick is a factor of 10 smaller or larger than the next one. And this allows the display of the longest and shortest wavelengths on the same plot. Now, one of the things that's interesting about light is that it can also be tied to temperature. So temperature is a measure of the average kinetic energy of the particles making up something. And so if the particles were not moving at all, you'd be at absolute zero. And there are several temperature scales out there. There's 3 that are commonly used. There's the Kelvin scale, which is 100 degrees between the freezing point of water and the boiling point of water, but starts at absolute zero. So that's the one that's used in science, because measuring from absolute zero has a whole bunch of convenient properties. Let's please sign in. And then there's the Celsius scale, which goes from the freezing point of water at 0 to 100 at the boiling point of water. That's used in most countries of the world. And then there's the Fahrenheit scale, which has 180 degrees between the freezing point of water and the boiling point of water, and starts a little lower. And that scale is good for weather. And so different temperature scales are more useful for those things. We're mostly going to talk in Celsius and Kelvin in this course. And for astronomy, a lot of stuff tends to be very hot, so the difference between Celsius and Kelvin is negligible. Yes. Yes. So, if something is 10,000 degrees, the fact that you'd add 200, about 300 degrees to go from Celsius to Kelvin doesn't really make a difference. But yeah, to go from Celsius to Kelvin, you add 273 degrees. But one of the things that's interesting is that anything with a temperature emits light. Because anything with a temperature has kinetic energy in its particles. They're moving around. Those jiggling around particles have charges and are accelerating, so they create electromagnetic radiation. So anything with a temperature emits light via what's called the blackbody spectrum. It's called a blackbody because it's what would be emitted by an ideal, perfectly black object that was at a certain temperature. And this is what a blackbody spectrum looks like. It has some peak frequency of peak emission. And this dotted line is more like what you'd see for a real spectrum, because in all likelihood, that light being emitted by whatever source you have is passing through some stuff that will absorb some of it. There are two laws that describe what blackbody spectrum is generated by something with temperature. First, the peak wavelength is inversely proportional to temperature. The higher the temperature, the shorter the wavelength. This is why if you get something really hot, you will see it goes, first it won't glow to your eyes, then it'll glow red hot, and then it'll start to glow like orange or yellow and eventually white hot. That's that peak temperature moving to higher and higher wavelengths. And so if you can measure where that peak temperature is, you can measure the temperature. And that's, if you've ever used an infrared thermometer, that's what an infrared thermometer does. It measures the infrared light coming from the object and works out where the peak temperature would be and uses that to figure out the temperature. You can actually get away with, because the blackbody spectrum has a certain shape, you can actually get away with just measuring at two wavelengths and figuring out the relationship between them to like figure out the slope, to figure out where the peak would be. The second is that the total energy emitted is proportional to the fourth power of temperature. The hotter something is, the more light it flings out. And that's proportional to the fourth power of the temperature. So it goes up real fast. And this means if you know the temperature of an object and how much light it's flinging out in total, so this is energy per unit area that is proportional to temperature to the fourth power. But it means if you know the temperature and how much light something is putting out, you can figure out how big it is. So that's how we figure out the size of stars. We figure out how much light they're emitting. We figure out their temperature by looking at where the peak of the blackbody spectrum is. And then we can work out what temperature, how big they need to be to emit the amount of light that they're emitting, to be as bright as they are. So blackbody radiation, an ideal radiator, it would be a blackbody. And the radiation emitted will depend only on the surface temperature. So the two rules are the Stefan-Boltzmann law. Higher temperature gives you higher intensity. You can see how as we go up in temperature, the peak gets higher and higher. And Wien's law. Higher temperature moves the peak to a shorter and shorter wavelength. So you can also see here as the peak goes higher and higher, the wavelength gets shorter and shorter. It moves towards the left. And so, this is why white hot is hotter than red hot. So the electromagnetic, and this is how incandescent light bulbs generate light. This is how the sun generates light. This is maybe how the projector generates light. I don't know. But other types of light sources can use other methods. So the electromagnetic spectrum is more than just visible light. Light has a dual nature. It can be both a wave and a particle. And radiation laws tell us how the spectrum varies with temperature. Now, so we're going to talk about types of spectra are when you study how the light you're observing varies with wavelengths or frequency. And we're going to talk about different types of spectra. So white light is composed of all the colors of the rainbow. If you run it through something that separates them, like in a prism, different wavelengths will be bent by different amounts in a prism, and that will split light into its component colors. Something very similar is happening when you see a rainbow. Different colors of light are bent by different amounts in raindrops, and that causes the colors to separate, and so you see a rainbow. It's actually quite a bit more complicated, but that's the general idea. The same effect is causing the fact that different colors bend by different amounts when they pass into a prism or when they pass into raindrops. It's just the exact process by which you see it has several extra steps for a rainbow. So a spectroscope is a tool that splits light into its components colors. So you have light, you have a lens to line all the light all pointing up in the same direction. You run that narrow through a slit. You run your narrow beam of light into a prism or some other thing that separates the wavelengths. And then you can focus it on a screen and you'll see different colors spread out. It's the same as shining a light into a prism to see a rainbow, only more precise. You want to have a very thin slit that you run into it, so stuff doesn't overlap and it makes it fuzzy. So the thinner the slit you get, the sharper the differentiation is. And there are several ways you can do this. That you don't have to use a prism. Sometimes we use prisms, sometimes we use diffraction gradients. But that's the general idea. Use something that will split it into the component colors. So the spectrum is useful for a number of things. There's two things you can really see in the spectrum. There's the black body spectrum from some hot object. That tells you the temperature and the brightness of this object, which is very useful information. But there is also spectral lines. So if you looked at the black body spectrum emitted by, I don't know, something like the sun, the light from the sun passes through a bunch of stuff before it reaches your spectroscope. And that stuff will absorb some of the light. So what you'll see is dark lines in your black body spectrum. And those dark lines actually correspond to the elements that absorb the light. So by looking at the spectral lines, you can find out about the composition of stuff. So you can figure out what the stars are made of by what absorbs some of the light. Also, because these are tied to elements, they're the same everywhere. So if they're offset from where they should be, this ties to the Doppler effect, and that lets us measure the velocity of the stars. So spectral lines give us lots of information. They tell us what the light has passed through, and they also can tell us how fast things are moving. So there's three basic types of spectrums. There is the continuous spectrum. This is the black body spectrum. It's formed by a solid, a liquid, or a dense gas. There's no breaks in the spectrum. It's visible light. You'd see red through violet. It's got all electromagnetic radiation in it, from gamma rays through radio waves. So this is emitted by anything that is hot. So like an incandescent bulb, stars without their atmosphere, things like that. This tells you about temperature and brightness. Next, there is what's called an emission spectrum. So an emission spectrum is how you generate light in a different way. Neon lights generate an emission spectrum. What you can do is you can take an atom and you can excite one of its electrons in various ways. In neon lights, you do this with an electric field. But you excite one of its electrons, it goes up to a higher energy level within the atom, and then it falls back down. When it falls back down, it will emit light because it's effectively being accelerated. And that light will always be at the same wavelength. So for neon, it'll always be at a number of different wavelengths depending on how it falls back down, because it could fall back down in one step or it could take a few steps. And the wavelength corresponds to how far it falls down, basically. So neon, for example, if you excite neon and it falls back down, it emits a bunch of light in the red, which is why neon lights that use neon are red. You get other colors by using different gases, different elements. The fluorescent lights in this room use mercury, which emits ultraviolet light, which then hits a powder coating on the inside of the light, which absorbs that ultraviolet light and re-emits it as visible. But an emission spectrum will have just thin individual lines with emptiness in between. It's not all wavelengths, it's a handful of them. LEDs also look like this. So only specific wavelengths are visible. These are bright line spectrums. In general, they're emitted by an excited gas, like a nebula. Also, I mean, if there's actually a layer of the sun's atmosphere that's emitting an emission spectrum, because it's being excited by the sun. It's totally washed out by the light from the sun underneath it, but during an eclipse, you can sometimes see it, or if you use a special telescope that blocks out the bright layer, you can see the thin coronosphere. Not chromosphere, not coronosphere. I mix up some terms. So emission lines are single frequencies emitted by particular atoms. And the emission spectrum can be used to identify elements. Each element has a unique pattern of lines it generates because it has its own energy levels. And so they have fingerprints. Each one corresponds to a fingerprint for a particular element. So here's neon. You can see there's lots of red lines in it. You ever seen those old, really yellow streetlights that kill all color? Those are sodium lights. Sodium has a really strong pair of lines in the yellow. And here's hydrogen and helium. And here's mercury. Mercury has some very strong lines in the ultraviolet, and that's why it gets used in these fluorescent lights. And it's also why you need to be careful around broken fluorescent lights, because they contain mercury. And then, so we talked about what happens if you have an electron falling down when it got excited. Well, the opposite thing can happen as well. If you have light hitting an atom, it can excite an electron, and that will absorb some of the light. And that creates an absorption spectrum. And so this is little dark lines along that black body continuous background. So this is formed in a continuous source. It's viewed through, say, a cooler gas. Specific wavelengths get removed, and you have a dark line spectrum. This is also the type of spectroscopy that gets used all the time on Earth for things like chemical analysis and stuff. because different molecules have different patterns of absorption. So, if you want to identify what this strange white powder is that you found on a crime scene, you'll use spectroscopy. It's one of the ways you can do it. So this is emitted by many astronomical objects. Anything that has an atmosphere will have an absorption spectrum. So stars and planets all do. And that allows us to analyze those atmospheres. We can tell what's in them by looking at the spectrums. So that's how we know what some of the atmospheres of distant planets are, or even planets in other solar systems. We've been able to take their spectrums and figure out, what they're made of. So these are probably the most useful type of spectrum. So if a continuous spectrum passes through a cool gas, that gas will absorb the same frequencies that it would emit, and you'll get dark lines. Now, here, if you have a bunch of different things in your atmosphere, you get lots and lots of dark lines. So here, for example, is the absorption spectrum of the sun. It's really complicated. Also, it turns out if you have molecules, their spectrums are much more complicated. Because it turns out there's a whole bunch of other places the energy can go. So you get much more complicated spectrums. So like atomic hydrogen has that very simple spectrum I showed. Molecular hydrogen has a much more complex one. But this is the absorption spectrum of the sun. So a continuous spectrum is emitted by a solid, liquid, or a dense gas. An emission spectrum is emitted by a diffuse gas that's excited by something. It's usually really hot or being hit by bright light from a nearby star or something. And an absorption spectrum is emitted when light from a continuous source passes through a cooler gas. And this happens all the time because it just needs to be in the way. And here's sort of a quick illustration of the Kirchhoff's laws. You have a light source that gives you a continuous spectrum. If that light source hits a gas cloud, it can excite the gas cloud to give you an emission spectrum, but also it can pass through the gas cloud and give you an absorption spectrum. And we can use this to determine many properties of the stars and other astronomical objects, which is why every major telescope consists of like an imaging thing and a spectroscopy thing. So if you ever look at what has this telescope got? If you, in parts, it's like, here are our instruments. We have our thing for looking at stuff, and then our thing for taking spectra, and our thing for looking at stuff at another wavelength, and our thing for taking spectra at those wavelengths. There's three types of spectra: continuous emission and absorption, and Kirchhoff's radiation laws tell us under what circumstances each of these will occur. So let's talk about how those spectral lines form from atomic structures. So this is an atom. This is a cartoon that is not actually accurate to what a real thing looks like, but atoms are made of three things: protons, neutrons, and electrons. The protons and neutrons are in the nucleus, which is tiny and in the middle. The protons have a positive charge. The neutrons have no charge, but they help hold the protons together in the nucleus. So at the scale of the nucleus, there's another force called the strong nuclear force that can interact between protons and neutrons, or even protons and other protons. And it helps hold them together because otherwise they're all positively charged and crammed into a tiny space. They want to fly apart. So you have to have some other force that holds them together. And then on the outside, we have the electrons. They orbit around, they're attracted to the positively charged nucleus, and they orbit around effectively, and they have a negative charge. So they're on the outside. So they're what interacts with other atoms. So all of chemistry involves just electrons between atoms interacting with each other. So very rarely stuff with nucleus happen. When we create active nuclear activity, things go boom. But well, not always, but yeah. So when we talk about atoms, we can talk about two different variations of atoms. What element you have is determined by the number of protons in the nucleus. So if there are 3 protons in the nucleus, you have lithium. There are 2, hydrogen, 1, helium. But there are also isotopes. Isotopes are nuclei that have different number of neutrons. So here we have some examples with helium. The most common form of helium has 2 protons, 2 neutrons. It's nice and happy and stable. However, a small portion of helium is helium-3 with 2 protons and 1 neutron. It's lighter. It has some slightly different properties because the spin of the nucleus is a little different. But the main difference for an isotope is a different number of neutrons, so a different mass. So this is helium-3, it's lighter. The way it is, you say the element name and then the mass, 3. So this is helium-3 because 3 things in the nucleus. Helium-4 has 4 things in the nucleus. And then these are very rare, and I'm not even sure if they're stable. Helium-5 and helium-6. So helium-5 has 3 neutrons with its 2 protons. Helium-6 has 4 neutrons with its 2 protons. These are getting too many neutrons and probably want to spit some of them out. These 2 are stable. This is the most common. Helium-3 is very expensive, as I know from some personal experience, because my PhD research was on helium, and one of the things we were doing was changing the amount of helium-3 in the mix to see what happened. So we had to be very careful with our supply of helium-3 because it's rare. Because it's a small portion of helium. Helium is annoying to get on Earth because you have to get it from natural gas deposits. Because otherwise, if you release it into the atmosphere, it just leaves. So that's one of the ways you can have different types of atoms. Those are isotopes. The other thing you can have is you can have ions. Ions are same nucleus, but they have a different number of electrons. So this is normal helium. 2 protons, 2 electrons. It's neutral. If it gets ionized, you add or remove an electron. This is ionized helium. I got rid of an electron. So this would be helium plus. It has a positive charge. It's +1. If I added an electron instead of removing one, it would be helium -1. So electrons, some atoms, it's very easy to knock off or add or remove electrons. They ionize very easily. These are things like sodium and chlorine. Both sodium has a very loosely bound electron, and chlorine really, really wants another one. So if you put them together, sodium will give chlorine its electron. Sodium will end up positively charged. Chlorine will end up negatively charged. They'll stick together and you get table salt. You would like the sodium and chlorine to be ionized and tied together, because on their own, sodium and chlorine are not things you want to personally interact with. Chlorine is a nasty toxic gas. Sodium reacts violently with water. So the existence of spectral lines required a new model of the atom. And basically what happened was, to have these spectral lines and have these spectral lines always be the same, we couldn't have sort of freely floating electrons. And Niels Bohr was able to put together a model of the atom where electrons were only allowed to be at certain energy levels. You could only have certain orbits with certain energies. So the ground state, the lowest energy level, is like this, and then you have an excited state with a bigger orbit that's above it, but you can't go anywhere in between. And the fact that you have to jump from one to the other with a little packet of energy is where the term quantum comes from. Quantum means like lump or packet or step. I don't remember exactly the etymology, but that's where the term comes from. So here are some of the energy levels for hydrogen. Bohr did hydrogen first because it is the simplest atom. It has one proton and one electron. It's super simple. So the electrons have distinct energy levels. They can only move between energy levels. They can't be in the middle. And going up to a higher energy level takes energy. That creates an absorption line. And going down from a higher energy level gives off energy. That creates an emission line. So the wavelengths we see if you excite hydrogen are actually this series going down to the number 2 level. Because going down to the number 1 level, all those energies are the wavelengths. All those energies are too high, so the wavelengths are too short. You see, the bigger the step, the smaller the wavelength, because that's a higher energy. So these are all in the ultraviolet. These are in the visible, and these are in the infrared. So what we actually see is what's the Balmer series here. This is the distinct red line that's pretty common. So moving to a higher energy level takes energy, moving to a lower level gives off it. And so emission energies, they correspond to energy differences between energy levels. So the modern model of an electron, instead of the electron really being in a nice circular orbit, it's in a fuzzy cloud around. And that cloud can have some weird shapes. But again, there are energy levels. And the high, yeah. Sorry, the lower energy levels. It's actually they're usually referred to as higher energy levels. Yeah, the higher energy levels tend to be further away from the nucleus. So this is the ground state. This is the excited higher energy level state. It's a cloud that's further out. Now, some of these have weird shapes, and then when chemistry gets involved, those shapes change because the atoms interact with each other, but yeah. So only specific wavelengths can be emitted or absorbed, and this creates a fingerprint for each element. Now, when you have a molecule, there's a whole bunch, the electronic states get a lot more complicated, and so the fingerprint gets a lot more complicated. So these are, individual elements. Are these labeled? I don't have labels on these. Oops. I think that first one is hydrogen. I'm not certain on the second one. So if you have an excitation, something hits it, it jumps up to a higher energy level, and then it drops back down. That's direct decay. That's sort of the simplest way you can get this to happen. But you can also have a cascade. You can jump up from the ground state to not the second state, but a higher state. And then it can come down in a series of steps. And when that happens, what you get is your input light could be ultraviolet, but your output could be visible. That's actually what the fluorescent lights in here are doing. That powdered coating is designed so that it absorbs ultraviolet light, excites the molecules into a higher energy state, and then they come down in a cascade that emits visible white, a whole bunch of different frequencies of visible light to give us white light. And an absorption spectrum happens when you go the opposite direction. Light comes in, knocks an electron up, and it gets absorbed. And if you've got more than one electron, your spectrum gets a lot more complicated because there's a lot more possible states. Because you've got a whole, here, for example, there's 6 electrons. You could knock one of these 4 up. You could knock one of the inside ones up. It gets complicated. And ionization, if you knock one of the electrons free, that changes the energy levels and changes the spectrum. So you could measure how much ionization is going on by looking at spectrum. And then when you have molecules, stuff gets a lot more complicated. On the bottom here, that's atomic hydrogen. Above it, that's molecular hydrogen. All I did is add a second hydrogen and let them bond. But now, that hydrogen, the 2 hydrogens together have so many more ways they can jiggle. So you get so many more lines. In an object like the sun, this gets very complicated. Different ionizations give different spectrums, and molecules give more complicated spectrums. So the solar spectrum is very complex, but we can find every element we can find on Earth in the spectrum of the sun. Including some that we couldn't find on Earth, like helium was first discovered in the spectrum of the sun. Which is why it's called helium, or Helios, the sun. So atoms are composed of protons, neutrons, and electrons. Electrons can only be in specific energy levels around the atom, and each atom has its own distinct fingerprint, which lets us determine the composition of astronomical objects. So lastly, let's talk about the Doppler effect. The Doppler effect is a tool we use to measure the movement of objects with light. So you may have heard something speed past you, and the sound it makes changes as it speeds past you. So it turns out that any moving wave source will affect the pattern of waves that come from it. Basically, if a wave source is moving, the waves get bunched up in front and spread out behind. So in the direction of motion, waves get bunched up. Opposite the direction of motion, they get spread out. So this depends on the relative motion of the source and the viewer. So either the source could be moving. So if the source is moving towards you, the waves are going to get bunched up from your point of view. But if you're moving towards the source, you're going to see the waves faster because you're going to hit them faster than they were emitted. So they'll appear to be bunched up as well. So that shortens the wavelength. So a moving source will affect the pattern of waves that come from it. In the front, waves get bunched up. Behind, they're spread out, as you can see in this little animation. And it depends on the relative motion of the 2 objects. So either the object could be moving or the observers could be moving. But here, if we have an object that is moving, if it's moving away from you, you'll get what's called a red shift, where the wavelengths get longer. And if it's moving towards you, you'll get a blue shift, where the wavelengths get shorter. And we hear this in sound as well. When something is moving towards you, it's a higher pitch. When something is moving away from you, it's a lower pitch. And this is also used, you may have heard of Doppler radar, but you also may have been caught in a radar speed trap. Radar speed traps use the Doppler effect to measure the speed of your car, because they bounce the light, they bounce a radio wave off your car, and how fast your car is moving affects the shift of the bounced off wave, and you can use that to calculate the speed. And Doppler radar does a similar thing, bouncing radio waves off of raindrops, and lets you know how fast the rain is moving, and you can figure out how the wind is moving. So the Doppler effect only measures how fast something is moving towards or away from you. If something is moving sort of across your field of view at right angles, it's not going to have any Doppler effect. but it's going to be moving across your field of view, so you'll be able to see it move. So it turns out we can combine the motion we see with the Doppler effect to figure out the actual speed of an object. So it doesn't measure velocity across the line of sight, it only measures velocity towards and away from it. The Doppler effect shifts an object's entire spectrum towards the red or towards the blue. So you'll see that fingerprint of spectral line when you look at a star. You'll see that fingerprint of spectral lines. So the pattern you expect to see, you'll still see that pattern with the same spacing, but it will have been shifted either towards the red or towards the blue, depending on whether it's moving away from you or towards you. So here's an example. Here's the spectrum you'd see in the lab. Here we have the spectrum redshifted. Unfortunately, yeah, here's the line here. It got cut off. I don't know why this is cutting off. Everything is shifted a little towards the red. And here is a blue shift. Everything is shifted a little towards the blue. So it's called a red shift because it shifts towards longer wavelengths, so it shifts in the red direction. Doesn't mean it actually appears red. Does mean you get a funny bumper sticker that says, if this bumper sticker appears red, I'm driving too fast. And a blue shift is the opposite. If it's, it'll be shifted towards shorter wavelengths. And in general, the shift is not super huge, but it gets bigger. The size of the shift depends on how fast you're moving. So the faster you're moving, the bigger the shift. Here's the formula for calculating it. The change in wavelength over the initial wavelength is just the velocity of motion over the speed of light. So you're not really going to need to do any calculations of this. I just wanted to show you the formula. General idea is the bigger the speed, the bigger the shift. And you can tell whether it's coming towards you or away from you. So if you have a spectral line in the star, observed to have a wavelength of 656.5 nanometers. And at rest, this will be at 656.3 nanometers. The velocity of approach or recession, well, it's shifted to a longer wavelength, so it's going away from us. And the velocity will be equal to the speed of light times the change in wavelength over the initial wavelength. So 300,000 kilometers per second times 0.2 nanometers over 6.56.3 nanometers, or this object is moving away from us at 91.4 kilometers per second. That's the radial velocity. It's not necessarily its true velocity through space, because it might be moving side to side as well. So it might be going even faster than that. So waves are affected by the motion of an object. You get a red shift that shows an object is moving away, and a blue shift shows an object is moving towards you. And the Doppler effect can be used to determine the velocities of objects in space and allow us to figure out how fast things are moving. So that's the end of chapter 5. Remember that a wave has a period, a wavelength, and an amplitude. Electromagnetic waves are created by accelerating charges. The visible spectrum is different wavelengths of light. And the entire electromagnetic spectrum includes radio waves, infrared, visible light, ultraviolet light, X-rays, and gamma rays. And you can tell the temperature of an object by measuring its blackbody rate. And a spectroscope splits light beams into its component frequencies. Continuous spectrum is emitted by solid, liquid, and dense gas. Hot gas has a characteristic emission spectrum, and a continuous spectrum incident on a cool, thin gas gives you an absorption spectrum. And spectrum can be explained using atomic models with electrons occupying specific orbitals, and emission and absorption lines result from transitions between these orbitals. And the Doppler effect can change the perceived frequency of radiation, and it depends on the relative speed of the source and the observer. So that's all for today. Any questions?
No.
So, yes. So they're on Brightspace in the section called worksheets. So if you go to Brightspace and click on content, you can go to homework and worksheets. And the worksheets are right here. Yeah, and they're just quizzes. Brightspace. But you get as many attempts as you want. They're just intended as homework. They're called quizzes because that is what Brightspace calls the answering questions thing. Yeah. Okay.